by clause allows you to specify a list of order items, and each order item consists of a column according to which you want to sort, and the sorting direction can be ascending or descending. Now, this statement ensures that the output of your query is sorted by those columns that you specified here. So in order to determine the sorting order between different result rows, the database management system, we first look at the first order item that appears in your order by clause. And then for those rows which have the same value in the first order by item, it will look at the second order by item and sort by that. And if it also has the same value there, then it will look at the third one and so on. So the priority for sorting is on the items that appear earlier in your order by clause. And there was some question about in which order things are applied in general. For the order by clause, it is applied after the where condition, for instance, is evaluated, and also after grouping has happened. And that is important because if you have a group by query, then into the order by clause, you can only put the columns that are guaranteed to have the same value for any group. So basically, you can only use the columns in the order by clause where all rows in the same group are guaranteed to have the same value. And that means that as long as we're talking about columns, those essentially must be columns that appear also in the group by clause. Because if a column appears in the group by clause, it is guaranteed that all rows in a group have the same value for that column, because that column is used in order to define groups. So this is a bit similar to the restrictions that we had for the select clause. Once we have a group by query, then there's also certain constraints on what you can put into the select clause. You can also only put columns into the select clause, for instance, that are guaranteed to have the same value for all rows within a group. And that also means that in practice you want to restrict it to columns that appear in the group by clause. All right. Now the limit operator, that one is pretty intuitive. I simply give the database system the maximum number of results, rows, and then this limit clause is applied at the very end of query evaluation. All right. Now in the following, we're going to discuss more and more advanced features of SQL queries. First of all, I want to discuss a little bit more about NUM. null values. Now, we have already quickly mentioned null values a couple of times. A null value in SQL simply means a value that is currently unspecified, for instance, because it is unknown. Now, those null values, for instance, influence the way in which SQL evaluates Boolean conditions. Typically, you would think of those Boolean conditions as evaluating either to true or false. But if one of those conditions contains a null value, then the overall result of the expression could also be unknown. And we will see a couple of more concrete examples for that in the following. Now, this is how we can essentially check for the evaluation result of one of those Boolean expressions. You can check whether it is true or whether it is false. Careful, if you want to check whether the evaluation result is null, whether the evaluation result is unknown, you cannot simply write equal to null, but you need to write is null in order to check for that. And then if you have any rows in your data that where the condition being the where clause, for instance, evaluates to null as opposed to true, then those rows will not be contained in your query result. Now let's make a couple of concrete examples. I encourage you to try out at least some of those examples either in your local Postgres installation or using the website that I have shown you last time, which doesn't require any local setup. Perhaps the first one, we can do it together. If we have a query of the form that you see here, where we want to know whether 3 equals null. Does anyone have propositions for what the result of this query could be? Syntactic error, okay. That would be one possibility. It's a little bit more permissive than that, actually. Okay, there's different propositions, null, empty, okay. So, does anyone want to explain in the chat, please, why they think, for instance, that the result could be a syntactic error? Or why the result could be null, for instance? Typing out an explanation like that takes a little bit more time. So let me resolve that. So the correct answer here would actually be null. And I expected that perhaps some people write false as a proposition, but that has not happened. I guess one could at first view think that the result here could be false because I have an equality condition and I have different things on the left side of it and on the right side of it. Now the problem is this. Those null values represent an unknown value, so they are placeholders, so to speak. That means if I write 3 equals null, it essentially asks whether 3 is equal to some unspecified placeholder. But the placeholder, as it is unspecified, we cannot be 100% sure whether it isn't 3 by coincidence. So here I'm essentially asking whether 3 equals to some unknown value, and whether that is the case depends on that unknown value. And since we cannot decide whether this is true or false, the answer to this query would indeed be null. Okay, there's a couple of other examples here. Yeah, and somebody is posting how that looks like in Postgres into the chat. So those null values in Postgres, they are just represented as empty spaces. So here you have one row, but you don't see any content, and that's because this row only contains one null values. So null isn't a value like in other languages like Java. So there is some differences between Java null values and SQL null values. I mean, in particular, you couldn't perform certain operations with Java null values because at some point you might get an exception, null pointer exception from the Java system. So here in SQL, in principle, you can use null values wherever you can use other values as well. The only thing is that if you have a null value somewhere, it might mean that if the null value is contained within one expression, it might make the result of the entire expression unknown, meaning null in the end as well. And null is like false in this case, so that depends on which case you are referring to. In some cases, so if you are referring to the semantics, if you have a null value as a result in the where clause for one specific row, then I fully agree having a null there is treated in the same way as if the result had been false. So if the entire condition in the where clause evaluates to null, then the corresponding row will not be included into the query result. All right. So, okay. So now maybe you had a little bit of time to try out some of those examples. I believe it is relatively quick to try because you don't need to type a lot. And yes, so we have already discussed about the first one. The second one is also null as a result because we are essentially asking, is one first unknown value the same as one second unknown value? And of course it depends on the unknown values. The third query null is null. That is always true because is null is checking whether something is unknown. And in this case, it is indeed unknown. The next query is the opposite of that and therefore false. Now perhaps the last two queries are still interesting. We have true or null, and in this expression we do have a null value appearing. However, an or expression is true as soon as at least one of the components is true. And in this case, one of the components definitely is true. Therefore, the end result does not really depend on the unknown value. And therefore, the end result of this should also be true. On the other side, for the last query, we have true and null. That means if the unknown value is also true, it makes the entire expression true, but if the unknown value is false, it makes the entire expression false. So the result depends on the unknown value, and therefore the result is also unknown. So this is what is called SQL's ternary logic, because all logical expressions can have three result values: true, false, and unknown. And the question is, what should select null? Is null due if the predicate is true? This query, frankly, is not very useful, admittedly. So this is just for the sake of an example. In practice, this query, it's not interesting. It essentially has a constant result, right? And by the way, also note that here we are not using any data source in order to calculate the result of our query, so we don't have a from clause. Depending on the database management system, some of them disallow that. You always need a from clause, but in Postgres you can write queries like that do not depend on any data in your database, but just evaluate constant expressions. All right. Now, and the is keyword, quick question here still. So the is keyword, it is more precisely the is null expression. So that essentially checks whether the expression on the left-hand side of it evaluates to null or not. And it is true only if the left-hand expression evaluates to null. So null equals null is null, but null is null, that is true. Alright. So it is basically not only a single is keyword, but it is null. That is a fixed command. Both words together. Alright. So now that we have discussed in more detail about null values, we can discuss more about some extended variants of the join. So far, we have been looking at joins that essentially retrieve pairs of rows from two tables that match together, meaning that they satisfy some kind of join conditions. For instance, we have seen the example where I'm pairing up the students with the enrollment information for the courses that they are enrolled in, and always matching together those rows which have the same student. Now, one problem with that is that it eliminates the rows in a table which don't find any matches in the other table. Those rows will not appear in the join result. So if I'm, for instance, joining students with enrollment information, then a student who hasn't enrolled into any courses yet will not appear in the join result at all. And this is not what I want in some cases. Perhaps I want to, for instance, encourage students to enroll for courses who have not enrolled yet. But in order to do that, I first of all need to make sure that those students remain in the join result, such that I can see that they haven't enrolled in any courses yet. And SQL offers you some specialized syntax in order to make sure that the result of a join keeps all the rows that appear in the input tables, even those rows which do not have any matching rows in the other table. And that is called an outer join. Now, for instance, for students and enrollment, the result relation of the join between the students and enrollment contains columns for the student ID, for instance, but also columns for the course ID, for the enrollment. And the question is, if we want to keep those students without enrollments in our join result, what should we fill in as values for the course ID column? And this is where null values come into play, because those outer joins will fill in the values for rows without matching rows in the other tables. They will fill in those missing values with null values again. So if you have those students who haven't enrolled into any courses yet, then the course ID and the corresponding join result will be set to the null value. This is the syntax that you can use here. You can write in the from clause of the query some first table, left outer join, some second table on some join condition, and that is guaranteed to keep all the rows of the table on the left side of each join. There's also the complement, the right outer join, where we say that all the rows on the right hand side of the table are kept in the join result. And if you're interested in keeping the values, the rows for both tables, you can also use the so-called full outer join. And very quickly, I'm gonna show that to you. So if we have, for instance, database where we have those tables with students, courses, and enrollment, then we can, for instance, select all columns from the students, left outer join with the enrollment information, and here I should still add the join join condition, which is on the student ID, right? And here you see the result of this join. Now here, for instance, the student Bob seems not to be enrolled in any courses. That is why the course ID is left empty in Postgres, and that always indicates a null value. Here, by the way, I had also inserted before a student with unspecified student name. So that's why here we have the student ID for that student, but the name has not been assigned yet, and also the student has not been enrolled in any courses. That is why we have empty fields here as well. So this is how the result to an outer join looks like in Postgres. Now back to the slides here. So let's also see a little example here in the slides. One thing that I might want to do, for instance, especially for instance, I want to remind students who have not enrolled in any courses yet, what I want to do is perhaps to count the number of enrollments for each student. In the following, you will see how we can do that with an outer join. So here for the moment, we are using the same database that we have used in the previous lectures of students with enrollment information and courses. And as you see, for the moment, we're not using any outer join, we're using a standard join. And that means that students without any enrollment would be filtered out by this query, which is not what we want. So already we probably want to replace this join by a left outer join that is guaranteed to keep information about each student. But now the problem is that we are currently using a count statement, and I just see that some group by statement in this query has been left. So here I actually want to add a group by statement for the corresponding query. So that unfortunately has dropped. So here we want to group by the student name in order to count the number of enrollments for each student. And the problem that we still have here is that for the moment we are counting the number of result rows. That means for those students for which we don't find any matching enrollment information, we will still count one result row for those students, which is not what we want, because for those students we want to count 0 enrollments. So the last thing that we need to do in order to make this work is that we replace the count star, which counts any result row, by count CID, which only counts those result rows that have a non-null, meaning a noun value, in the course ID column. So if a student doesn't have any associated enrollment information, then after the outlet join, that student will have null values in the course ID column. And if we use this counting variant, then those rows with null value for the course ID will not get counted. So I will get a count of 0 for those students who have no enrollments yet. All right. So this is some useful join syntax that in practice, every once in a while, you might need some of that. I'm also going to post the corrected example on Piazza. Now, in the following, we're going to look at a little bit more advanced SQL features. And one powerful feature of SQL is that you can write queries which combine multiple other queries together. So you can essentially write composite queries that essentially combine multiple smaller SQL queries in one way or in another. And the easiest way probably of doing that is with the SQL set operations. So if you have a result of the queries, then for instance sometimes you might want to take the union of the result of two queries. And with SQL you can do this using the union or union all keywords. And essentially here in this specification, query 1 and query 2 refers to queries, for instance, like the ones that we have seen so far, but then you can compose them using the union keyword, for instance, into a larger query, and the result of the query is essentially the union of the results of the two contained queries. What is important here is that those two queries, query 1 and query 2, they must be compatible, meaning that their results have the same structure, so it has to have the same number of columns and also the same column types. There's a couple of different variants. If you use the union keyword, for instance, then SQL will automatically eliminate duplicate rows that appear in the union result. If you use union all, for instance, then it will keep any duplicate rows. You might have the same result row multiple times. You also have operations for intersecting the results of queries and for taking the set difference between two query results. But in all of those cases, you must be careful because the result structure of those different queries that you are combining with the set operations must be compatible. All right. And a priori, there's a question about whether the order will be kept when using a union. So in general, without putting the order by clause, you are not guaranteed anything about the result order. So if you want a specific result order, then you can still use the order by clause. And by the way, some of those operations, some of those set operations, they are, for instance, not supported in some other common database systems, but if you try it with SQL or with the website that I have shown, then you will be able to run those operations. Alright. Now, another thing that we will start discussing today and finish the next time probably is that we can essentially not only combine queries with set operations, but we can essentially use so-called nested query in many other parts of a query as well. For instance, so far we have seen that in the from clause of a query we can refer to tables that appear in your database, but instead of that you can also write a new query inside of the from clause, and we will see some examples of that. Also, for instance, you might use queries as part of a condition in the where clause, and so on and so forth. So in general, since queries take SQL relations as input and produce SQL relations as output, you can compose them together in various interesting ways. Now, if we have the situation that we have one large query which is containing a smaller query, so to speak, then we also call that a contained query the subquery as opposed to the containing query. It has different variants of that containment. In the simplest case, finished next time probably, is that we can essentially not only combine queries with set operations, but we can essentially use so-called nested query in many other parts of a query as well. For instance, so far we have seen that in the from clause of a query we can refer to tables that appear in your database, but instead of that you could also write a new query inside of the from clause, and we will see some examples on that. Also, for instance, you might use queries as part of a condition in the where clause, and so on and so forth. So in general, since queries take SQL relations as input and produce SQL relations as output, you can compose them together in various interesting ways. Now, if we have the situation that we have one large query which is containing a smaller query, so to speak, then we also call that a contained query the subquery as opposed to the containing query. It has different variants of that containment. In the simplest case, the subquery is essentially self-contained. So you could run this query independently and it would work with your database management system. That is what we call an uncorrelated subquery. But for more complex expressions, you can actually make the subquery refer to elements outside, to elements of the containing query, and those cases are a little bit more difficult to understand. That is what we call correlated subqueries. Now, in the following, we're going to first discuss about the uncorrelated subqueries, which are a little bit easier to understand. And we start with a rather trivial SQL. We can essentially not only combine queries with set operations, but we can essentially use so-called nested query in many other parts of a query as well. For instance, so far we have seen that in the from clause of a query we can refer to tables that appear in your database, but instead of that you could also write a new query inside of the from clause, and we will see some examples on that. Also, for instance, you might use queries as part of a condition in the where clause, and so on and so forth. So in general, since queries take SQL relations as input and produce SQL relations as output, you can compose them together in various interesting ways. Now, if we have the situation that we have one large query which is containing a smaller query, so to speak, then we also call that a contained query the subquery as opposed to the containing query. It has different variants of that containment. In the simplest case, the subquery is essentially self-contained. So you could run this query independently and it would work with your database management system. That is what we call an uncorrelated subquery. But for more complex containing a query, it has different variants of that containment. In the simplest case, the subquery is essentially self-contained. So you could run this query independently. And it would work with your database management system. That is what we call an uncorrelated subquery. But this contained subquery is essentially self-contained. So you could run this query independently and it would work with your database management system. That is what we call an uncorrelated subquery. But for more complex expressions, you can actually make the subquery refer to elements outside, to elements of the containing query, and those cases are a little bit more difficult to understand. that is what we call correlated subqueries. Now in the following, we're going to first discuss about the uncorrelated subqueries, which are a little bit easier to understand. And we start with a rather trivial and frankly not very useful example here. So we simply want to select the names of all students. Then I can, of course, simply use the students table in the from clause. But just to illustrate the principle of subqueries, I can also put a new subquery into the from clause, as you see here. So here essentially I have one entry in the from clause which corresponds to a subquery. It's an entire query right there. And what it does is essentially just selecting the student names from the students, and then the result of that subquery is named SQ for a subquery. And as you see in the select clause of the query, for instance, I can refer to the name for the subquery that I have just introduced. So that is important. Postgres actually will force you to assign names for subqueries that appear in the from clause, because typically if you use tables in the from clause, then you always have a name, and I can use that name in order to refer to specific elements from other parts of the query. But if I write a new subquery, then a priori it doesn't have a name yet, so Postgres forces you to specify a corresponding name. And so how that is handled depends a little bit on the database management system. In each case, this query is not yet very interesting, admittedly, so let's see something a little bit more useful. And here we have a subquery in the where clause, for instance, and what we are doing here is that we are selecting the names of students where the GPA is greater or equal to the maximum GPA among all students. So here we are selecting the students with the highest GPA, and here we essentially use one subquery in order to calculate the largest GPA over all students with the maximum aggregation function, and then we are using the result of that query within a condition in the where clause. And here the question is whether the result of that query would not be just one student. That depends actually, because multiple students might have the same GPA, and very good, I see somebody is giving that same reply. So in general, by the way, so I think this is great. I see that often there's some discussions in the chat. I want to encourage that. I often see great replies to the answers from other students. So please feel free to post not only questions, but also replies to the questions of your peers in the chat. I think this is working very well. All right. So this was the first example for subqueries, and here things are already becoming a little bit more useful. So today I wanted to take a little bit of time to show you how to apply SQL in order to actually analyze, do at least some simple analysis of a data set in practice, the full cycle basically. I encourage you to try it out yourself. So I mean, SQL, it's something which is a little bit like a programming language in that it is much easier to understand it if you are experimenting with it yourself. So I encourage you to do that. Now, the next time we're going to see a little bit more advanced features of SQL, in particular when it comes to subqueries. And then we are going to start with a new chapter. We're going to start looking at how the database management system internally processes your queries. Right? Thank you, and have a nice day. Good. So, hello everyone. Today we are first going to talk a little bit more about SQL, and probably we will still have enough time to start with a new topic, which is about looking at how your data is actually stored on the computer. Now, last time we have seen one very important feature of SQL, which is that you can essentially nest SQL queries, so-called subqueries, within a larger surrounding query. So you can use a SQL query as part of a SQL query, basically. And the last time we've seen a couple of very simple examples for that. Here you see one of them. Here you're selecting the student names from the students table where the GPA is greater or equal to the maximum GPA across all students. And in order to calculate this maximum GPA, we are actually using a subquery. So here we have one query marked up in red here, which selects the maximum GPA from the students table. And then the result of that query is used as an operand within the where condition of the surrounding query. So that is one possible use case for subqueries. We can also use them in other parts of a query. All right. Now, in the last example, we have seen one possibility to include a subquery into a larger query. There's many more ways in which you can do that. Here you see a couple of more ways in order to integrate subqueries into the where condition or into conditions in general of your query. And one operation that you commonly use in the context of subqueries, that is this exists expression here, and that essentially checks whether subqueries, we can also use them in other parts of the query. All right. Now, in the last example, we have seen one possibility to include a subquery into a larger query. There's many more ways in which you can do that. Here you see a couple of more ways in order to integrate subqueries into the where condition or into conditions in general of your query. And one catchword, one operation that you commonly use in the context of subqueries, that is this exists expression here, and that essentially checks whether the result of a subquery is empty. You also see some more examples on that. So that is commonly used. Or for instance, you could check whether one specific value is within the result values produced by a subquery, and you can do this using the in keyword that we have already seen, but so far we have seen it for checking whether one value is within a list of constant values, and here we are using it to check whether one value is within the results returned by the subquery. Another thing that you can use is the all and any keywords, and here essentially you use that in order to test whether some condition is satisfied either for all result rows of a subquery or for any, meaning for at least some of them. And in that case, the corresponding condition returns true. Let's perhaps see one more example for the last possibility here. What we are doing here is we are selecting the student name from the students where GPA is greater or equal all result rows from this subquery that selects GPAs from students. And can anyone tell me in the chat what you believe that this query is doing? Anyone, any ideas? Yeah, exactly. So here I have multiple propositions. Yeah, so multiple times the same propositions actually. So that is correct. So here we are again essentially checking for those students where the GPA is greater or equal the GPA of all students. So in the end, that comes down to searching for the students with the maximum type GPA. Yeah. All right. And one last question is whether the result of this, I assume it means the result of the where expression, whether that can be false or null. So here, I mean, it could be null if we have, for instance, some null values for the GPA. If there are some students that don't know the GPA, I cannot verify whether one specific student has the highest GPA because I don't know the GPA of some of the other students, right? And I mean, for this to be false, that is the case if there is another student who has a higher GPA than the currently examined students. You can imagine that here we are iterating over the students that are stored in a student table. We are picking one, then we check whether this condition that student's GPA is greater or equal the list of all GPAs from all students for each of them. And if that is the case, I'm going to include it into the result. If that is not the case, I'm not going to include it into the query result. Right? So we can essentially imagine that we have a for loop pretty much where we iterate over the students, and then the subquery would essentially correspond to another for loop. So we have like essentially two nested for loops. Both of them are iterating over the students. Yeah? Okay. All right. Now, those are a couple of examples for subqueries. Essentially, you just evaluate the subqueries first for the examples that we have seen, and then you get some kind of return value. Then you insert that return value into the surrounding query. Now, what we have seen so far is what we call uncorrelated subqueries. And that means essentially that you could run the subquery all by itself and the database management system would not complain. Correlated subqueries are a little bit more difficult. This is why we are doing them now, and we started with the the other ones. For correlated subqueries, the nested query, the subquery, is not independent from the surrounding query. So here the subquery would essentially reference some elements that appear in the surrounding query, which means that a subquery all by itself is not viable because it would include references to something that only exists in the outer query, right? And so here, by the way, I see some interesting discussion going on, and I encourage you to generally answer the questions of your classmates also in the chat. And just because I see that here, let me say one last thing about the evaluation of this subquery that I have shown here. I told you that you can imagine that this is evaluated by two nested for loops, and here one of the questions is, wouldn't that be inefficient? And I actually agree with that. So if I say that you could evaluate it with two nested for loops, I just mean conceptually, this is how you can imagine what the query result is going to be. You can essentially, in order to understand what the result of this query is, you can imagine that we would have two nested for loops. But internally, the database management system is probably doing something more efficient, or could be doing something more efficient. And the way in which you write your query generally is independent of how the database management system evaluates your query. So the two for loops, this is not necessarily what's happening inside, but this is what you can imagine is happening in order to understand what the result of this query is. Okay, very good points here in the chat. All right, and now we are switching to correlated subqueries which reference something outside of the subquery and in the surrounding query. Now, let's see the first example. I need to move the chat so I can see the example fully. All right. So here we are again selecting the student names from the students table, and we assign the alias S1 to it in the outer query. And the condition to be included in the result is that the S1.GPA must be greater or equal to all. And here comes a select over students again. This time we assign a different alias S2. And we require that S1.SName equals S2.SName. So can anyone first of all tell me why this is a correlated subquery? Looks kind of similar to the ones that we have seen already, so what makes this one specific? Yes, very good. And here there's the reference to, in particular, S2. So within the, in particular, S1. So here within the subquery, we are referencing table alias S2 and table alias S1. Now, table alias S2 is not particularly exciting because that is defined within the same subquery. Table alias S1, on the other hand, that one is actually not defined within the subquery, but it is defined outside. It is defined in the outer query. That means if you take the subquery, select S2.GPA from students S2, where S1.SName equals S2.SName, that subquery marked in red, and you run it all by itself in the database management system, you will actually not be able to do that because the database system will complain to you that there is some undefined identifier S1. And that's why it is a correlated subquery. So yes, so this is why it is a correlated subquery. And can anyone guess as to what this query is actually doing? So strictly speaking, we have not yet discussed in detail how to evaluate those correlated subqueries, but maybe anyone has a hunch about what this could be. Very good. And here I see the right solution popping up. So what it does is actually the following. So I'm again gonna tell you how you can imagine that this query is evaluated, even though internally inside the database system, it might be evaluated in a more efficient manner. But what you can imagine here is that we are iterating in the outer query, we're iterating over the students again. And for each of those students that we are iterating over in the outer loop, so to speak, we are iterating over the students in an inner loop. And within that inner loop, we are only considering students which have the same name as the currently selected student in the outer loop. And then we check whether for all of those students which have the same name as the students in the outer loop, the GPA from the outer loop student is greater or equal to the GPA of the inner loop student. S1 and S2 basically, those are like two iterator variables. Okay, and because of that, as suggested here by one of your peers, we do indeed retain those students, the name of students which have the maximum GPA among all the students with the same name. So that's maybe a little bit of an artificial example, but of course, in principle, you can have students with the same name, even though not the same net ID. And here we are keeping the maximum GPA student among all groups of students with the same name. One thing that I used here, by the way, besides introducing correlated subqueries, I have one query where the same table appears multiple times. We have already seen that before, but just to point your attention towards that. So in general, you can have the same table appear multiple times in a query, either within different subqueries or even like within the same query. But what you often want to do is to assign different aliases to that same table. So here I have the students table, once appearing with S1 and once appearing with S2. And one interesting question that I see here, whether this query would be possible without two aliases to students. And here, I mean, if you want to, I mean, you could probably reformulate the query in quite a different way, and maybe you could get around that. But I mean, definitely as long as you stay with this structure of the query, here you need to compare students of the same name. So you need to compare two students, and in order to distinguish between those two students, you need to use an alias here. Yes, exactly. So that's why I'm saying that if you keep the same structure, then you need to do this. It would also be ways, for instance, to group by the names, get the maximum GPA in each group. That is a great suggestion, and then joining that with the in order to get the student associated with the maximum GPA within each of those student groups. Or you could, for instance, use a subquery in the from clause, and then you would have to introduce an alias for that subquery, but strictly speaking, not for the table alone. Okay, so there's many ways of writing this, but you need some way of correlating different students in order to make this comparison. All right. So the general principle, in order to imagine how the result of those correlated subqueries is generated, I find it quite convenient to imagine nested loops being evaluated, even though that might be inefficient and not what the database management system is doing in the background, but it can help to imagine that. And then you would generally iterate over the rows in some outer containing query. And for a fixed row, you would evaluate the inner query. Now here, the result of the inner query might depend on which row is currently selected in the outer query. That is why, at least conceptually, you would have to re-evaluate the correlated subquery for each different row in the outer query. And then if the where condition in the outer query uses a subquery, then finally you would decide for the currently selected row in the outer query whether to include it into the result set or not. Whether to include it into the result set or not. Outer query, whether to include it into the result set or not. Now, here, for instance, we have another example. So here again, we are comparing students, and we use a correlated subquery. So here, we, in the outer loop, iterate over the students again. And then, for each fixed student in the outer loop, we check whether the result of this correlated subquery is non-empty. That is what the exists keyword is doing. There exists some result. And for a fixed student in the outer loop, in the inner query, I'm iterating over the students again. And I check whether there is another student who has a higher GPA. Now, and if such a student exists, then the outer loop student will be included into the result set. So what is this basically doing is that here, this time, we're selecting the names of all the students except for the students with the highest GPA, because for each student we test whether there's another student with a higher GPA, right? So those are a couple of simple correlated subqueries that you see here. Now, take a look at this one. Now, what I'm exploiting here is the fact that actually your subqueries can also have subqueries. So you can have multiple levels of nesting. And here, in this query, we are first iterating over courses. Then next, we are iterating over students. Then next, we are iterating over enrollments. Does anyone have an idea what this query is doing? Any propositions? Okay, first position, find courses that have no students enrolled in them. Find the courses that have no enrollment. Okay, other propositions? In order to break that down, so that is perhaps the most complex query we have seen so far. Okay, so let's break it down a bit. So let's make it simpler by imagining that we have already fixed one course in the outermost loop. Now, can anyone tell me what the result of this select star from students and so on, what the result of this query is gonna be? So we have fixed the course, and now we have this query select star from students as where not exists select star from enrollment E, where course ID matches and student ID matches. Find courses with at least one student enrolled. Okay, that is all right. This is the right direction here. Okay, I'm gonna give it a second because I think it's a nice example and makes sense to think about it for a few seconds. Okay, good propositions here. Okay, I'm gonna resolve it in a minute. Just okay, people are agreeing. Is that agreeing to the solution, perhaps? Okay. All right, so I give it one more minute and just think about it a little bit more. And clearly, as the exists keyword tests whether the result of a subquery is non-empty. Not exists essentially tests whether the result of a subquery is empty. And it is true only in that case. All right. So let's have a look at this. So let's maybe start with the innermost subquery. So what we're doing here is that we're looking at the enrollment information which links students to the courses that they are enrolled in. Okay, and the student as well as the course, they have been fixed in the outer queries currently. So here I'm essentially checking whether some enrollment information exists for the currently selected course and for the currently selected student. Now, this innermost subquery is contained within a not exists clause in that middle query, which selects from the students table, right? And so basically here in that middle query, I'm producing students which are not enrolled in a specific course because the enrollment information for this student with the currently selected course in the outer query is empty. Okay? So here, let me maybe mark that here. So here, this query essentially looks for students that are not enrolled in the currently selected course. And now I'm looking for courses where the result of this subquery is empty. So I'm essentially looking for courses where no student is not enrolled. So that formulated differently means that here I'm looking for the students, for the courses where all the students are enrolled, which most likely is empty, the result of that query, but that is what the query is looking for. Here I'm fixing a course, then I'm looking for students which are not enrolled in that course. And then I'm checking whether that list is empty, so no student is not enrolled in the course. And if so, I'm including the name of this course into the result set. That's what this query is doing. All right. So that is what we will see about SQL. Now this is probably the most difficult query that we have seen in the course, and I encourage you to think a little bit more about it and to make sure that you understand what's going on there, and also perhaps to experiment a little bit with some with some nested queries yourself. For instance, in one of the data set that we have recently downloaded, or in some other data set of your choosing. We have seen a couple of examples, but in the end, to really get the hang of it, you probably want to write some queries like this yourself. And I encourage you to do that. So now we have seen essentially what is the interface of database management systems. And now we will see in the following a little bit more